This is lab 8 for ENME351, so here's part 1, the comparator. Here's a circuit all set up with the op amp and the LED. As I rotate the potentiometer, you'll see right now it's at this really dim state, and as I rotate it, it will suddenly switch to a much brighter state. So you can't really see this transition, it's just going through these two different saturated states, and it's basically following this graph. So the slope here is really steep, so you can't really see that transition on the LED, and it's just going from really dim to very bright. Here's an analysis of the non-inverting op amp. So going through looking at each node, we know that Vin and V plus are going to be equal. And also we can use a voltage divider to find V minus. So using this voltage divider with R1 and R2, we can get a relationship there in terms of V out. And then since we know that V plus and V minus are equal, we get that relationship in terms of V in and V out. So ultimately the gain, V out over V in, will be 1 plus R2 over R1. Exercise 2, the unity gain amplifier. This is a circuit all set up, so we have the potentiometer, which will be turning to change V in, and in this case V in is equal to V plus, so that goes directly into the op amp, and additionally all of the wires are color coded according to the table given. So here we have the processing screen. So right now V out, which is equal to V minus, is shown as blue since they're overlapping, and then V in is equal to V plus, which is shown as yellow since they're overlapping as well. So right now V in is 0 volts, and you'll see there's kind of a gap, and as we move up and get to that 2 volts, you'll see that both the blue and yellow dots start to move together, so V in is equal to V out, as we would expect with this unity gain amplifier. So one of the reasons that there might be that gap towards the beginning is we're not going through a full range of -5 to 5 volts, and rather just 0 to 5. So the inverting amplifier. Here's the circuit, and once again we're using the potentiometer for V in, which is going to be going to V minus, and it's going to be going through 2 resistors. One is of 10 kilo ohm value and the other of 1 kilo ohm value to create that -10 gain in the closed loop. Additionally, we have a voltage divider here using 2 1 kilo ohm resistors to keep V plus at a constant 2.5 volts. So all those wires are color-coded again, and now I'll show the screen. So if it can focus. So right now, it was at its lowest V in, so it was set to 0. I'm slowly turning it up. You can see that V plus is stuck at that 2.5 volts as it should be. And once we kind of reach this 2.5, and get a little bit above it, you'll see that's when V out starts to drop. So V out is able to reach its max when we instead turn V in below 2.5 volts, so below V plus. With the inverting amplifier, the way V minus is behaving when V out reaches its max, it's actually equal to that 2.5 volts. So V minus equals V plus when V out is at its max. So here's the analysis of the integrating amplifier. This is what it looks like, and basically you're going to do nodal analysis right here at V minus. So we know that V plus and V minus are equal, and V plus is 0. So going off of that and doing nodal analysis, you'll get ultimately that V out equals negative V in over the impedance of the capacitor times the resistance. So you'll have to do inverse Fourier transform to this, and you'll ultimately get that V out in terms of time is going to be -1 over RC, so -1 over tau, in the integral of the input voltage. The final integrating amplifier, I have it set up here on the circuit using the capacitor and also the resistance that was specified. So you can see that as I turn the potentiometer in this case, and we look at V in, which is equal to V minus, so green, V out is mimicking kind of this pattern as it's down here, and then when I get closer to 2.5 volts, V plus, V out is getting to its max, and then once I cross, it suddenly will drop and stay around that value.